Hello, ladies and gentlemen. What we're going to be doing today is we are going to be taking a look at something called Faraday's Law. We've talked about already how um, how a current carrying wire can induce a magnetic field, and now we're going to look at the opposite of a magnetic field inducing current. So you'll go through this slide presentation. Make sure you complete day 12 exit ticket by 2:30. And then you will be doing day 11 and 12 assignment. Hopefully yesterday you just did the first page. If you got a jump start on the second page, that's fine. But you'll be using this PhET simulation here. I have a link here. And then I'll also have a link on Google Classroom as well, where you can get into it on the exit ticket. Okay, but this assignment or this lab or this PhET simulation, you are actually going to be using your answers from this PhET simulation, from that worksheet on the second page there, and you'll just be plugging in all of your answers onto a Google Doc. So you can either just create your own Google Doc and just type in the answers if you want to just do number 1 is this, 2 is this, 3 is this, 4 is this, or you can copy and paste the entire second page there. I'm not 100% sure how that would look, if everything would copy over with all the pictures in there and everything, but you can give it a try. All right, so question for today is, if current can create a magnetic field, can magnetics create a current? And I kind of answered that already, and the answer is yes. All right, we can do either or. This is Faraday's law, saying that any change in the magnetic environment of a coil of wire will cause a voltage, or another thing we call this is EMF, which is an electromotive force to be induced into the coil. So we are basically inducing current into the coil. All right, so take a little bit closer look at this electromotive force. If you were to take a magnet and move it next to a wire or a coil of wires, it is going to induce current into the circuit. Okay, so a couple ways that you can do this is you can change the number of loops on a coil. You can change the cross-sectional area of the loop. You can change the magnetic field, the strength of the magnetic field in Teslas, or you can move the magnet faster, or basically you increase the velocity. The faster you move the magnet through the loop of coils, the more current you're going to induce into that coil. All right, so if you want to take a second and go and tinker around with the PhET simulation right now a little bit, you can go back to that slide that had the link on it, and you can tinker around with that a little bit just to kind of see what the setup is that I'm talking about here when I'm talking about number of loops, or the cross-sectional area, things like that. But we're literally just taking and creating a circuit, just like you normally would any circuit, but you're taking wires in the circuit and you're just creating creating a giant coil, almost like it would look like a spring, and you can send a magnet through that coil, and that's what's going to induce current into that circuit. Okay, here's the equation we would use for our electromotive force. EMF is what we said is it's induced voltage is what it is. So we actually measure EMF in volts. And then we have what is delta. Now delta is just a change in something. So I want you to recall that from last trimester. That just means a change in something. That doesn't actually represent any sort of variable. Okay, that's just Greek letter delta. So it's a change in one of these three things. Either N, capital N, which is my N is, number of, it's sometimes called number of coils or number of turns. Okay, so the number of turns, or the amount of turns that the coil has. Um, and that obviously has no unit label to it. You can call it turns if you want to. And then A is your I'll call this cross sectional area. And that's the cross sectional area of the size of your loops. All right, now those loops, it might be, it could be a square, it could be a circle, and just keep that in mind as you're going through. I believe we end up on your worksheet that I will have for you tomorrow. Ends up using, I think it ends up using circles a lot. So, and then we have B, which is your magnetic field. Magnetic field, and remember that is just measured in Teslas. Oh, sorry, I forgot to say, with cross-sectional area, that is going to be measured in meters squared. Has to be in meters squared. If you're ever given centimeters or anything like that, you have to convert it to meters first before you find that cross-sectional area. Okay, and then we are dividing that by time. So basically what that is saying is we're changing one of these three things, and then you're doing that in a certain amount of time. So the time is basically representing your velocity or how fast you are doing that. Okay, so let's move on to, oops, that is not what I wanted. All right, so moving on to this example here for what we might see in one of our problems. Sorry, I'm trying to get back to this view. So consider a flat coil with 5 loops. The coil is 20 centimeters on each side and has a magnetic field of 0.3 teslas passing through it. The plane of the coil is perpendicular to the magnetic field. The field points out of the page. Now, for this part right here, I'm actually just going to cross this off because we are not going to be worrying about a question I took out here. There was a letter C here that I took out. It asks you which direction does the current flow through the coil, and we have to use a version of our right-hand rule. I'm not going to have us worry about that. So we're not going to worry about which direction the current is flowing as you're moving it through a magnetic field. We're just not going to worry about it. Okay. So what we have here is the first question says, if nothing is changed, what is the induced EMF? Or basically it's asking, what is the voltage induced? Okay, well, if nothing is changing, remember our equation was EMF is equal to a change in number of turns, area, or field divided by our time. Well, if nothing is changing, basically we're not doing anything over a period of time. So what this would end up doing is it would end up making your time 0 seconds. And we can't have that. So what we would end up having is we would just have 0 volts induced. Because if we're not changing anything in a certain amount of time, your electromotive force is just going to be 0. Okay, B says the magnetic field now increases uniformly from 0.3 teslas to 0.8 teslas in 1 second. So now I'm increasing my magnetic field. So while this change is taking place, what is the induced electromotive force, or what is the voltage? So using that same equation, now I can say my change in coils area and magnetic field divided by time, that is going to be equal to, we have 5 turns, and then we're going to multiply that by my area. Now keep in mind, we're not given area, so you need to be able to solve for the area of whatever it is you're given. So here we have a square, so it's going to be solving for the area of that square. We have 20 centimeters. Reminder that we want it in meters. So I'm going to do 2 meters multiplied by 2 meters. and that should give you cross-sectional area of 0.04 meters squared. So I'm going to multiply that by 0.04. And now I'll multiply this by the magnetic field. Now we are changing our magnetic field, so we're not going to specifically use 0.3 or 0.8. I want to use the change in magnetic field, so I'm actually going to end up with 0.5. And then I'm going to divide all that by my time, which is 1 second. Take a second to figure that out. Hopefully you end up getting 0.1, and then we are solving for EMF or voltage, so we have 0.1 volts. Okay, so your homework for the day, or your assignment for the day, is going to be, remember to finish that exit ticket, and your exit ticket is going to be using this PhET simulation and filling out that second page, or filling out using that second page of the day number 11 and 12 assignment. Okay, and then tomorrow we will have a little bit more practice with using the actual EMF equation. Okay, make sure if you have any questions to email me or send me a private message in Google Classroom. Have a great day.